Okay, so the assignment 2 architecture looked like this. We'll start with a bit of review of assignment 2. So we had a game engine class, or a game class, that held all the systems, and that held the entity manager, which held entities, which held components, right? So we just boot up the game, we're straight into the game. There's no menus, there's no different gameplay scenes, it's just game, right? So we had that one class. We had components. I'm going to go a little bit quickly through these because we talked about these at length. The components were pure data. They're stored in the entity class. Each component is its own class, and each component sort of has some intuitive English description behind it, right? Like this is the transform. It holds all the things that transform the position and scale, etc., of our component. We have a shape. That's the shape that gets drawn. We have a lifespan. We have an input, etc., etc. The entity then is anything in the game. It stores that component tuple in this contiguous, or ideally contiguous structure. We have a tag, which is the entity type. We have this active Boolean or a live Boolean, which is whether or not the entity should live or die. And we have this ID as well, which lets us tell if one entity is equivalent to another entity. Then we also have the entity manager. This is sort of that factory class that produces and manages entities for us. One of the biggest things that it does for us is it delays these actions such as add or delete so that we don't have any iterator invalidation, so we don't need to worry about that. So what the entity manager really does for us is this separation of data from logic, right? So we don't need to worry about how it manages all this data when we're trying to do our gameplay programming. And it also does this thing where it allows us some efficiency. So we trade a little bit of memory for efficiency by saying, okay, I'm going to actually store 2 copies of each pointer to the entities. And what that does is allow me to say, hey, get all the bullets in constant time, rather than having to filter all of the entities, very few of which may actually be bullets. And so we can do other bookkeeping. We can say, hey, how many entities am I creating per second or whatever? All that can be done in the entity manager. And then we had this game, this top level object. And what this did was it held all the game data, right? So over here we can see it has the window, it has the entity manager, it has whether or not we're running the game, stuff like that. So this held all the game systems as well. So down here we can have movement system, user input system, enemy spawning, etc. It held all of the gameplay code, and so the game class was really the whole game, right? And we'll see how we're going to get away from that in a bit. And then we also had this vec2 structure, which is the structure we're writing 2D games. So we have this 2D vector with an x and a y that can do all sorts of cool stuff for us, translate back and forth between SF vector 2f. You can add them, multiply them, whatever you want to do. So that was the architecture of assignment 2. And back when I gave this lecture, I guess 2 or 3 lectures ago, where you saw these before, we asked, what can the engine do? So it can create game objects as entities. It can add components to entities so that we can, make them do things that we want to in our game. We can implement the gameplay mechanics as systems, handle user input. It can play and pause the game, and it can initialize itself and load stuff from a configuration file, etc. But what are the things that we would want to be able to do in a more fleshed out game engine that we can't do with stuff in assignment 2? So one thing we can only do is we can only display one scene. So I already mentioned this a little bit, but what if we wanted a menu? What if we wanted an options menu? What if we wanted different types of gameplay in our system? We currently do not have any good way of loading texture and sound assets. You're writing arbitrary C++ code, so of course you could load textures and sound assets. But what I'm saying is the game engine architecture does not allow for doing this in an easy way, right? So we're going to talk about that. We cannot display textured animations, so we can't have Mario running around in an interesting way. We don't have any menu. Well, that's not true. I guess we have IamGUI, so we could make some weird sort of menu. But you know what I'm trying to say when it comes to a menu. And so this idea of a game scene, so games can contain many different scenes that have very different logic and controls. So this example over here comes from bonus point if anyone can tell me which Pokemon game this is. I don't actually know. Okay, so we got one Pokemon nerd out there. That's good. I haven't played anything since like Silver, so it's been a while for me. So an example, you may have like a menu scene where you're basically up, down, left, and right are just selecting things in a menu. But then later on, you may have an overworld map scene where up, down, left, and right now walk you around on a map. And then you may have a battle scene where pressing buttons do attacks or defend or throw potions or whatever, right? And so each of these, you can imagine, has wildly different programming behind them. And so we'd want to be able to separate those in a nice way, but all have them work well within our game engine architecture. And so how can our architecture allow for different game states? Well, we'll get into that in a bit. So in assignment 2, the game class handled all the functionality. And the thing is, a lot of the functionality, if you think about these different game scenes, a lot of the functionality that we want is still the same for each scene. It's just that things like game mechanics or user input are going to change, right? So there's still similarities there. So the game class for assignment 2 handled everything, but if we do want different scenes, maybe we could take advantage of like inheritance or something like that. So some of the things that were common to all of these scenes are, for example, we still have a main loop structure for our engine. That's going to be the same. We still have a game window, right? Everything, all the different scenes are still going to be drawn to that same window. We may still have that same game configuration file that specifies a bunch of different things. Assets, we may share assets, like Mario may be running around in this scene, also in that scene. Maybe we have music that's going to play during the title screen that's the same as during the gameplay scene. And so there is a lot of stuff that is common to all the scenes. And we wouldn't want to have 3 different scenes or 4 different scenes and have to replicate that code in 4 different places, right? So even though some of it is similar, there is stuff that's specific to each scene, right? So things like what the input does, that's going to be specific to the scene. The rendering may be specific to the scene. The game logic, collisions, etc. Like there's probably no collision code in the menu scene, right? Stuff like this. So in assignment 3, we're going to introduce the concept of separating all of these things. So we're going to separate the game class that we had for assignment 2 into 2 different classes that now separate the functionality. And so we're going to have the game engine class. And so the game engine class is going to be the thing that handles all the stuff that's similar between all the scenes. So it's going to have all that functionality that's present in all the scenes. So for example, the construction and the management of the scenes, how do we switch between the menu and the gameplay scene? Running and quitting the game, the handling of the window, etc. And then each scene class is going to have the functionality specific to the scene. It's going to have its own entity manager, right? Because each scene is going to have different entities in it, etc. So we're going to separate this. Now let's have a look at what these are. That should say game engine up there, but here's the game engine class. This is the top level game object. It's going to hold all the data that the game needs to run, right? Not the scene specific data, but all the stuff that the game needs to run. It's going to have, it's not going to have all game system functions. That is the wrong slide. So I apologize for this. I'll edit that later, but that's from the previous one. What the game engine is going to do, let me just ignore this text. I'll fix that later and I'll explain it from over here. So the game engine is going to hold data that all of the scenes need to access, right? So for example, it's going to hold a map from strings to scenes. And so what we're going to be able to do is say, hey, switch to the menu scene, and it will have that stored in its own scene. We're going to have the window here in the game engine. So the window is common to all the scenes, right? Because we're all drawing to the same window. Now, what you can actually do in SFML is open up multiple game windows. So if you have a project idea where you could have different windows, like that could be a thing. But for the most part, your game is going to be drawn to the one window. It's going to hold all the assets. So for example, it's going to load in a bunch of textures, load in a bunch of sounds, load in a bunch of animations. And then each of your scenes can access all of those things. Now, what we're going to do is load all the assets when we start the game, But if you have a game like Grand Theft Auto 5 that has like gigabytes and gigabytes of assets, what they will do, the reason that loading scenes exist is because there's not enough RAM to like hold every asset in the game. So if I switch from one place to another, there may be a loading scene where I load the assets that I need for this particular scene, right? But we're only dealing with a few megabytes of textures, so we're just going to load all of our assets at the beginning. We're going to store a scene. This is a string that says what's the currently active scene. So I could have multiple scenes that have been constructed, and I can switch back and forth, and this is the current one that I want to be able to view. And then I'm just going to store a Boolean to say whether or not the game is running or paused or etc. And then I'm going to have some functions here. All of these are pretty intuitive. One of them, change scene. That's going to allow me to change from one scene to another scene. Get assets, that's going to allow me to get access to this assets class that will let me draw a particular texture or animation. I have access to the window, and the base level user input is going to be handled at the game engine. So we're also going to do this thing, which I'll explain a lot more in the next lecture. Almost the entire next lecture is about this. But in the scenes where we're implementing gameplay, so let's say we have like Mario running around, right? We're going to, instead of saying, okay, I'm going to jump when the W key is pressed, I'm going to say, I'm going to jump when I've been told to issue the jump action, right? And so what we're going to do here is that the game engine is going to handle the literal parsing of user input, saying the W key was pressed, the mouse button was clicked, the space bar was clicked. But whether or not the jump action came from the mouse or the space bar or a network socket doesn't matter to the gameplay scene, right? It just needs to know when we're going to jump. And so we're going to see that we're going to separate literal user input parsing from the issuing of actions. And so this is going to handle all of that actual user input. Oh, look at this. Okay, so I have the actual thing here now. I forgot to delete this slide, so it's just an old slide. So let me go through that. Stores the top level game data, performs the top level functionality, changing scenes, handling input. It runs the main game loop, and the game engine pointer will be passed to scenes in the constructor so that the scenes can talk to the game engine and vice versa. Now, we have different scenes, right? And each of those scenes is going to have something that is unique to it. Otherwise, it wouldn't need its own scene. But we're still going to use object-oriented programming and say that even though each scene has its own unique stuff, there is stuff that's common to each scene as well. And so we're going to have a scene base class, and we're going to inherit from that. So what's the stuff that's common to each scene? For example, each scene is going to hold entities. So each scene is going to have its own entity manager, right? So if we just had one entity manager, how would we know which ones we're supposed to draw in this scene, right? So each scene is going to have its own entity manager. It may have its own frame count, so how long has this scene been playing? It's going to have its own actions that it can perform, like the menu scene might have move up or down, but the gameplay scene may have jump, shoot, throw a fireball, all sorts of stuff. The scene-specific functionality is going to be carried out in the derived classes of the scene class. And the scene class is abstract, and what this means, at least in C++, is that you cannot instantiate the base class of scene by itself. So by making it abstract, it says you can't instantiate a scene, you have to instantiate a derived scene. Okay? And this simulate function is going to call the update function. So the update function of a scene is going to do all of its logic, one loop, and this simulate function is just something that takes in a parameter and allows us to do that many iterations of the thing. We'll see why that's important a bit later in the class, but it just allows us to say, hey, for every rendering step, do 4 update steps of the logic, or something like that. Then the scene base class, why is this duplicated? Scene derived class, I made a mistake with the slides, but that's okay. The scene derived class, for example, scene play is going to inherit from scene, but that may just be like, this is the Mario running around scene, this is the menu scene. It's going to hold all the things that are specific only to that scene. So maybe the level that we're currently playing on, maybe the player pointer, maybe the configuration specific to that scene, etc. And the scene-specific systems are defined within the derived class, right? So if we have some animation, movement, enemy spawning, all these systems are defined within the derived class because we may have one animation system for the menu scene, but a different animation system for the walking around on the world map scene. Some derived classes of scene may require different systems based on the functionality, which I just said. And update, render, and do action must be implemented for each scene. So in C++, we can do this thing. When we define our abstract class, the way we make it abstract is by saying that some of the functions equal 0. So if I say this function equals 0, it means that this function does not exist, and so it must be implemented in the derived class. So I think Java does this with like interfaces or whatever, but we don't have interfaces in C++. So how do we do scene switching with this then? So the game engine is going to store a map from strings to shared pointers, right? So I just made this a bit smaller up here, but we have a map from strings to shared pointers. That's probably, my face is covering this in the video, so you can go back a couple slides if you want to see that. And it also stores a current scene string. And so we have a function, current scene, and what that does is it looks up the currently active scene, and then it calls that currently active scene's update function. So we know which scene we want to be performing right now, and it calls that update function. And so change scene string changes the scene to a new previously stored scene. And we can see here that this scene is scene function is templated. So if we need to construct a new scene, we know what type of scene to be constructed, and we can just construct that there in that function. And so what this is doing, if you think of a map from strings to things, it's basically just a finite state machine, right? So you've all seen a finite state machine. I go from this state to this other state. So maybe the game starts and I'm in the main menu, so that's the initial state. And then if I'm like hovering over the play button and I hit enter, we transition from the main menu scene into the gameplay scene, right? And if my character dies, I transition into the game over scene. If I finish the game, I transition into the credits scene. So it's just a state machine that has some logic from transitioning back and forth between scenes. So we have this function which is going to change the scene to a given string. And what's going to happen is, let's say, for example, I start up the game, I'm in the main menu. So I've got a main menu, I've changed some options or whatever, and now I'm going to change the scene into the gameplay scene. You have two choices here. Do you want to just overwrite the previous scene? Or maybe you want it to stick around for some reason. So let's take, I don't know, Legend of Zelda as an example. Maybe you have an inventory scene that handles like the world map and the inventory, whatever. And maybe you want to do something like, wherever my cursor was to equip that item, whenever I bring up the menu again, I want that cursor to be in the same place, right? So if I keep that scene around and I don't destroy it, then if I call change scene, if that scene's string already exists, I don't need to reconstruct that scene. It already is there. I just need to change the active scene to that scene, right? And maybe the gameplay of the other scene gets paused or something like that. But it just allows us to keep these scenes around if we want. But you don't need to do this. Like, you could also do it where you just store one scene pointer. That's the current scene. And then if I change scene, I just overwrite and destroy whatever scene I had before. But what we're doing by introducing this map here is just allowing several scenes to exist at once. So if I go back to the main menu scene, I still have the same thing selected when I went to this scene. And so the player is selected with the menu scene, and then the player selects a level on the menu. And so level path, that's the currently selected menu item. The menu tells the game engine to change scenes, and then we say, okay, game, change scene, change it to a gameplay scene called play, and then we have some arguments to that level, or to the scene that says load this level. Okay? So that's the game engine. It's a little bit much to take in just from a verbal description, but once you start using it, all you need to know is change scene. That's it. It's pretty easy. Next, we have asset management. So how are we going to handle all of our assets in the game? I'm going to show you, again, just to mention that, there's no one way to do this. I'm sure if you use Unity or Unreal, they're going to have a far more sophisticated, far more elegant way of doing this. But we have this thing that we're implementing from scratch, and it's going to be fast and easy and usable and learnable, right? So it's got to have all of those things in there. So assets, what I'm calling an asset for this game, it's an overloaded term, but what I mean for this is that assets are any external files that are loaded into memory to be used in the game. Okay, so for example, fonts, sounds, animations, textures, etc. Oh yeah, there we go. So we're going to have textures, which can be image files. We're going to be using mostly PNGs because they support transparency. And what can happen is you can have like an image of Mario or Mega Man or Link or whatever, and around Link will be all transparent so that you don't have like a big white box walking around your game, right? So that's why we're going to be using PNGs. But SFML supports the loading of any major asset type, so you could use JPEGs if you want. Animations. So what an animation is going to be is a texture with some bookkeeping. We'll talk about animations in the last half of the lecture. We're going to have sounds. The sounds that we are able to load in SFML are WAV files and OGG files. OGG is a lossless open source codec. You can't load MP3s because they're copyrighted or, it's always some sort of IP violation or something. So all of our sounds will be WAV or OGG for this course. And then fonts are going to be TTF files. And so that's what we're going to be able to load. And the key to using assets is to load it once and use it often, right? So if we have some fancy graphic for an enemy, we are not going, and let's say we have 1,000 of that enemy on the screen, we are not going to load 1,000 copies of that texture. We're going to load that texture once, and then we're going to use it a bunch of different times. We're going to point to that texture, right? So the amount of entities on the screen is not going to affect how much memory we use for assets. Of course, we'll have a bunch of different entities, so the entities and the components will take up memory, but we're not duplicating the assets. That's the important part. So of course, we're going to make a class. We're going to make an assets class, and what we're going to do is we're going to specify a configuration file, and in that configuration file, we're going to specify all the different assets that we want to load when the game starts. So for example, these are a couple of lines from the configuration file, the assets configuration file from assignment 3. So we're going to say, okay, this is one line. Load a texture, call it Mega Man, and then here's the path to the texture. Load a sound. It's called Megadeth, not the band Megadeth, but the death sound that Mega Man has. And then this is the sound path, right? So what we're going to do is store this in a map, right? We're going to have a map that stores strings to textures, that stores strings to sounds. And then I can say, hey, assets, give me Megadeth sound, and then play that sound, and it'll just work. And again, so for example, later on, what I can do is get those assets via the name that was specified in the config file. So I can say, hey, assets, get the texture called Mega Man. And again, just to let you know, these mapping of strings to things, if you were making, AAA game and you wanted as much performance as possible, you would probably have like enums or integers defining all of these things. But this, trust me, will not be the bottleneck in our performance, right? We're calling these things, it's one lookup in a map. It's not that bad. But just to mention it, if you were making a game as performant as possible, you'd probably have a vector with all of these things in it, with integer indices, and you'd have some big enum that specified all the different textures, but that's just a pain, right? So we're not going to do that for our game. And so to implement this, the asset class will have 4 different maps from strings to the type of asset that we want to store. So here's what the asset class is going to look like. We're going to have 4 private variables. Those are the maps for each type of asset that we want to store. And then we'll be able to add each of those assets and retrieve each of those assets. And the important part here is that the getting of an asset is going to return a reference to that asset. So whenever we get the texture, we're not duplicating the texture. Whenever we get a sound, we're not duplicating a sound. If we left off this ampersand, it's going to copy it, right? So make sure that we're getting a reference to these things, not a copy of those things. So this is going to live inside the game engine class, right? Because now we could have assets on a scene-by-scene basis if we had gigabytes and gigabytes of assets, but we're not going to for this class. We're just going to load everything in the game engine, and we initialize that inside the init function of the game engine class. And then in the scenes, we're going to have a pointer to the game engine class, and then we're just going to say get assets. So game, get assets, and then we get whatever we want from there. And the important part here, again, is that they're loaded just once at the beginning of the program. And assets can be used in any scene, but are only initialized once in memory. If I'm saying it 3 or 4 times, it must be pretty important. For larger games, like I said, you may want to load assets per scene, but we're not going to do that. And just saying here that, a lot of games have, especially on older systems, I walk from the inside of the castle outside the castle. There's a 2-second loading time because it couldn't store all the textures in the game, so it loads the things it knows it's going to need for that scene, and then does something else. Okay, so this is the new architecture. The next lecture is all about actions and user input and how we're getting away from this archaic move when you press W thing. But other than that, this is the game architecture that we're going to be using going forward. Any questions or anything about the architecture at all? I know it's hard to ask questions until you've used it, but okay. Yeah, make sure you only load things once. Now let's talk about textures and animations, because we're going to be using these for assignment 3 and 4. And even though assignment 2 didn't use any textures, we were able to do what I would call animation, right? So animation meaning a bunch of still images that make something, right? That make something move and it looks like fluid movement to you. But anything on a screen is not actually continuous movement. It's individual frames, right, that our eyes interpret as movement. And so you do have old things like vector-based games. So what we did in assignment 2 was kind of like these old vector-based games like Asteroids or whatever that just draw lines on the screen. So we can draw an octagon and make it look pretty and have it fire bullets and, explode into other things without any textures. But for the most part, any game that's, fun to play in modern times is going to have some textures associated with it. And this also allows you to outsource the creation of assets to actual artists rather than other programmers. So textures and animations are really important. What is a texture? A texture is a graphic that is mapped to a shape. And by graphic, I mean typically some sort of image file, right? So textures can be created dynamically or loaded from an existing file. What do I mean by dynamic texture generation? Well, what we could do is create a blank texture and then programmatically make it. So for example, all of you now, after having done assignment 1, would be able to create a checkerboard texture for me. You could draw a bunch of squares of alternating colors and save that as a texture in SFML. So that would be a dynamically generated texture, right? And you can maybe, if the player jumps, you could resize the texture or something. But we're going to just be loading them from a file. We won't be doing any dynamic texture generation for these games. And so a rectangular shape with a texture attached is typically called a sprite. And so a sprite has some texture, but also the extra specification of where in that texture I actually want to draw it. And we'll get into that more in a bit, but that's just a little detail. And sprites are very, very common in games. And it turns out that older computers, because they didn't have all this graphics memory, they didn't have dedicated GPUs, they had sprite hardware, right? So like the NES can only store so many can only show so many sprites on the screen at once. So if you're ever playing an NES game and sometimes the sprites are like flickering, it's because it can only draw so many sprites and it has to decide which ones am I going to draw now, right? Because it actually has hardware registers dedicated to sprite data, and older computers had this as well. At the very end of the lecture, the last slide is 2 video links, and if you're interested in games at all, it's very interested to sort of like, I'm a big believer in, to be good at something, you kind of need to know the history of the thing, right? It's good to know the limitations of who came before you so that you can truly appreciate what you're working with. And those are 2 videos that go into the details of how sprites used to work, what people, had to do on a Commodore 64, inputting the pixel data in a text file to draw Pac-Man and stuff like this. So I highly recommend watching those. But for us, a rectangular entity, not an entity in terms of ECS, but just like a rectangular shape, is going to specify where in a texture that this sprite's texture is going to be drawn, right? So for example, I could say, pick out the top part of this and draw that as a sprite, or pick out the bottom part of this and draw that as a sprite. And so that's what a sprite in SFML is. It's a texture that has been loaded somewhere, and then there's a rectangle that says where in that texture do I want to draw when I draw the sprite, and then the sprite is essentially a pointer to that texture. So if you have a single texture like Mega Man, you can create 100 different sprites based on that texture, and the sprites store a pointer to that texture. They never duplicate the texture. Okay, so that's important. Just have one copy of all of your assets, and that'll work well for us. So how do we load a texture in SFML? So we're going to specify a texture object, and then we're going to say texture.load from file, and then we're going to give it a file name. And I don't know, this probably none of you have done this. Who has worked in like raw OpenGL before? Okay, so maybe someone. That line, that's like 30 lines of code in like raw OpenGL, just loading an image. You've got to like import the zlib library for the compression scheme that PNG uses, and then, okay, is this 32 bits per pixel or is it 24 bits per pixel? And you got to specify all that and then create the buffer for all those. It's a noise. So this is one of the reasons we're using SFML, is because all the things that I don't want this course to be about, it just does for us, right? Because yeah, okay, loading of textures is an important thing for, AAA game development or super low level optimization, but that's not what I want this course to be about. So this load from file, that's going to return a Boolean whether or not it successfully loaded the file. So if you want to do error handling surrounding the loading of textures, this is how you would do it. You would say, if this returns false, so if not that, then I could handle an error somewhere. So for example, if you have a configuration file and you're loading all the textures from the configuration file, and one of them fails to load, you probably just want the game to exit and say, hey, I couldn't find that texture. Because you don't want like just a white square going around where your bullets should be or where your cloud should be. Oh, jeez, that's the worst. Maybe you do want a white square for clouds. But you don't want some blank texture because the game, like if it fails to load, it won't crash. It'll just, you have to handle that error on your own. Now, let's say we did want to create a blank texture and do something to it, like manually, dynamically create some texture. Well, we can create a blank texture, right? And by default, all of this will just be black pixels. So it'll just set them all to 0, 0, 0, and then we can do whatever we want with that. Once we've created a blank texture, if we want to, there are many different ways that we can modify that. I know that in person this may be quite small. I just wanted to include it all in the slides for reference. So here, this is how we would actually create a new raw array of pixels that we can use for a texture. And then we can update the pixels from an existing texture if we want to. We can modify that. We can update it from an SFML image. So there's also an image class. Or I can take the contents of a window and draw that to a texture. So I believe that SFML includes like a screenshot function. So if I press a button, I take a screenshot. But the way that works is it takes the render window buffer and saves it as a texture, and then it saves the contents of the texture to a file. So that's how that works. I did mention, though, that sprites are going to have not only a texture, but also we're going to specify a rectangle within that texture. Why? Why do we care about that? Why wouldn't we just take the whole texture? Well, by default, it is the whole texture, but there's something very important. We can specify a subrectangle of the texture which will be drawn. So when I load from a file, I can load only a specific part of that texture if I want to. Now, so there's two things, and it's a little bit confusing. One is this way, where, okay, maybe I have a huge texture and I only want to load a subregion of that texture. You would do that in this load from file. So I have this big texture, and I only want to load into my game a subregion of that texture. Another thing is, I want to load the whole texture into memory and then only draw a subregion of that texture. So this way, we're not going to be using this, because what that's going to do is have a whole bunch of different textures in memory, a whole bunch of different subregions. We just want to load one texture, the whole texture, and then specify which part of that texture to draw. Sometimes the texture will not be the same size as the entity's shape, right? So what do? Do we resize the entity? Well, that may affect gameplay. Do we resize the texture? Well, resizing the texture itself can be expensive. So what we can do is specify a subrectangle. That is me not selecting the whole word. There's no reason why that's black and this is red. We can specify a subrectangle that we want to be drawn. And so the entire texture will be loaded, but it's not all drawn. So that's what we're going to do here. And actually, this code up here is incorrect. That's not what we want to do. I do have the correct code on another slide, so I'll fix that. So here's an example. Our animations for assignment 3 are going to be a single image file, right? That image file is going to be as follows. So here are the 3 frames of animation in Mega Man's running animation. Well, actually, there will be 4, but 4 was a bit wide, so I just put 3 in here for the examples on the slides. So this is the first frame of animation. This is the second frame of animation. This is the third frame of animation. So the idea that we're going to have is that the animation of Mega Man running is going to be stored in a single texture, just a single PNG file. So you have Mega Man here, everything else is going to be transparent. And then what we're going to do is we're going to figure out when we want to play each frame of animation. And instead of loading a different file for each frame of animation, we're just, hey, this texture is already in memory. So I'm going to specify the rectangle that I want to draw for frame number 1. Then when it's frame number 2's time, I'm going to specify that rectangle. And then when it's frame number 3, so on and so forth, with just specifying the different rectangles. Now, what I've done for assignment 3 to make things a bit easier for you is that each animation is in its own file, and they all just go from left to right. If you go online, you're gonna I got slides on this, so I won't do it. So when you create a sprite, you're going to have a texture, this whole texture loaded in memory. So you say sfsprite sprite.setTexture texture, and then when you window.draw sprite, it's going to draw that whole texture. If these are the only 3 lines of code that you have, it will draw the whole texture to the screen. So in this case, it will draw all 3 frames of Mega Man, right? If you want to specify a sprite subrectangle, why do I keep including this? This is the wrong code. This is loading the texture in a subrectangle. I'm going to delete all of those when I post the slides. So ignore this. This is what we want. So a sprite has already specified which texture it wants to draw from. And if we want to specify a subrectangle to draw that from, here's how we specify that. So we say sprite.setTextureRect, and then we pass in an integer rectangle. So this would say go over by 10, go down by 10, and then it's 32 pixels wide and 32 pixels high. Okay? So it starts at 1010, it's 32 by 32, pick that. So the reason this works is because Sprite is a very, very lightweight object. So creating lots of sprites is very, very easy to do in SFML. And what happens here is that the sprite, this is the actual code. If you go on if you look at the source code of SFML, this is literally what a sprite is. So a sprite consists of 4 vertices. That tells you the geometry of the sprite, because the sprites are rectangles. Then you have a pointer to a texture. So it points to a texture. It does not copy the texture. The texture lives somewhere persistent in memory, and then it references it like this. And then you have that integer rectangle. And so by default, if you do not specify a rectangle, it just specifies the top left corner and the whole width and the height, so it draws the whole thing. But when you set texture rect like this, that's what gets specified. And whenever you say window.drawSprite, the GPU has that texture already loaded in memory, and it will draw the rectangle from that texture that you want. But just be very careful. It stores pointers to textures. So this is a cautionary tale. Let's say I wrote a function called loadSprite. That makes sense. I'm going to have a string file name. That's the file to the texture that I want to load. So and this is going to return a sprite object. So I'm going to set up a texture. I'm going to load the texture from a file. And then I'm going to create an FSS sprite based on that texture, right? So knowing everything that we now know about C++, what will happen if I run this function? Hand up if you know what's going to go on. Hand up, don't, yep. Yeah, so what happens here? We set up this RAII data structure, which manages the texture for us. The texture is going to load the texture, and then when the sprite constructs itself with that texture, it's going to store a pointer to the data that lives in that texture. And then it's going to return that object, but then it's going to exit the scope. Anything that was locally constructed in this scope is then going to be destructed. The destructor is going to clean up that texture, and now whatever this sprite thinks it's pointing to, that memory could be used for anything else right now. So what you have to do is load your textures in a way so that the texture object is persistent. And how are we doing it? We've got this assets class that stores it in a map, and it's always going to be there. Okay? So the pointer to that texture data is always going to be valid for any sprite that we create on any texture in our game. So you've got to make sure that the texture object lives as long as the sprite lives. And so this is very easy and intuitive code to write. Theoretically, it should work, but in practice, it does not work. Okay? Now you know why. And this is the sort of thing that you wouldn't get in a non-C++ language, because all of these things, like when it returns, it would not be destructed, right? You just have pointers to things. Sprite colors, I actually talked about these before, sprite colors and texture smoothing, so I don't need to talk about those again. I did that in the SFML lecture. Sprite transformations, so sprites can have a position set, you can move them, you can rotate them, you can set scale, you can scale them, so there's lots of things that you can do on sprites, but we've already talked about that. I'm going to get back into more texture stuff. So texture sheets. Has anyone seen texture sheets before, especially for older games? Yeah. So many games can have, or games can have many textures that will be used, and you don't want to have, if you have 100 different enemies in your game and each of them have 10 frames of animation, you don't want to have 1,000 different files, right? Loading from files is slow, or each time you load from file, it's not the reading from the disk, typically, that's the bottleneck. It's the fact that you're loading a different file. Then you've got a bunch of different files, a bunch of different textures in the GPU. Whenever the GPU wants to draw a different texture, it's got to swap some context. So it's better to have as few files as possible. So texture sheets can be used to store many textures within the same image, and then you can specify the rectangle that you actually want to draw from that texture. So it's an easy way to organize and store textures. And if the entire sheet is loading into graphics memory, less texture swapping occurs, etc. So here, this is Link to the Past, I believe. Yeah, I think it is, for the Super Nintendo. And so this is a sprite sheet. Now, I'm not saying this is how the Super Nintendo stores it. I'm just saying, here is a sprite sheet that you can use to have all of Link's animations in one sheet. And then I can say, oh, look, I want Link to run to the left, so I'll play this one, then this one, then this one, then this one, right? So I've got like 8 frames of animation for that. And so that's how you would do this. And I could say, oh, specify this frame, draw this one, then draw this one, then draw this one. Now there is some bookkeeping around knowing which subrectangle to draw, right? So I have to, at some point somewhere, maybe in a config file, say that these are the 8 rectangles representing the running animation or something like that. Here's another example of a sprite sheet. And so this is, people release these sprite sheet packs online. Sometimes they're free, sometimes they're paid. But if I wanted to make some, I don't know, Farmville, Stardew Valley type game, I might download a sprite sheet like this, and now I can build a house, because here's all the different textures I would need to build a house. And there's some doors. And, you know, I could make, here's the 9 different squares that you need to make any shape of lake, right? Because I could put a whole bunch of the middle ones and then put these surrounding it. And we're actually going to be doing that for assignment 4, so I won't do that right now. So instead of loading a different texture for every character, pose, or tile, or whatever, you just figure out which subrectangle you need to draw. And rectangles can be stored as variables, or they can be computed dynamically if we store the sprite sheet cleverly. So what do I mean by that? Well, for example, maybe I know that the top left of the water tiles start at this top left. So then I could specify this rectangle, but if I want to know where the top right one is, it's just that plus 2. If I want to know where the bottom right one is, it's the top right one down 2, right? So you can store them cleverly in a way that you can dynamically compute their indices. And so, for example, my texture for walking begins at this int rect, right? And then I could store that if I wanted to. So texture-based animations. Animations, of course, you all know, they're a sequence of animation, they're sequence of images, so sequence of static textures that, when played quickly, appear as motion to our eyes. We are very easily tricked. And it turns out that, you know, smooth motion occurs around 20 to 30 frames per second, right? So most movies that you've ever seen in a movie theater are filmed at 24 frames per second. And you're not saying to yourself, oh, that's weird. Like, why am I seeing like this PowerPoint presentation? Like, your eyes are tricked into that. But isn't it crazy how if you played a game at 24 frames per second, you'd want a new computer? Right? And the difference is motion blur, right? So if you have motion blur from a real life camera, it covers that like difference in the FPS. So, but if you've been playing games at like 120 or 240 FPS, then going back to 60 FPS looks like a PowerPoint presentation. So it's just what your eyes are used to. And so these texture-based animations are sometimes called bitmap animations or raster animations, and they're just made of pixels. So raster, bitmap just means that there's pixels in a rectangle specifying some graphics, rather than a vector-based animation, which is more like assignment 2, where we're drawing a shape and just rotating it, or some displays, like old displays for arcade games like Asteroids and other games, literally only draw vectors. So they can only draw lines, and everything needs to be made up of lines. They are not capable of bitmap animations. So how are we going to implement this? I've already told you how we're going to implement it, but the actual mathematical details are going to be displayed now. So here we are going to have this texture that specifies the entire animation that we want. So for example, this is Mega Man running. Maybe I call it Mega Run or something like that. So there's a file, megarun.png, and it specifies every frame of animation. And what's going to happen is we're going to want to play the first frame of animation, then the second frame, then the third frame, and then we loop back around to the first frame, second frame, third frame. And so we just play this in a continuous loop. And if we do that at a specific speed, it's going to look like Mega Man is running. So this texture is going to have some width and some height, right? And when we load the texture, we can say .size or .width or whatever it is in the API to get those values. And then we're also going to have some number of frames of animation. And this number of frames of animation is going to have to be specified in some configuration file, right? Because yes, we can figure out the width and the height of the texture, but there's no function that says analyze the image and tell me how many frames of animation there are. Maybe ChatGPT can do that now, but we're certainly not like running any image processing on this. So in a config file, we're going to say megaman or texture mega run, right? And load that image. Then we're going to say animation. It's going to use the mega run texture, and there are 3 frames of animation. So we've got to specify that animation which uses a texture that we've loaded. So the frame width in this assignment, this doesn't always work out if you download assets from the internet, but because I'm telling you this is how I've created these animations, and I created them all by hand from texture sheets. There's not many of them, so it wasn't too much work. But the frame width of 1 frame of animation is just the texture width divided by the number of frames, right? That's pretty obvious. And because of the way I've laid them out in just a horizontal line, the frame height is always going to be the texture height, okay? So the rectangle that we want to draw is specified by left x value, top y value, then width, and then height. And to get the exact rectangle, it's going to be the frame number, starting at 0, times the frame width, then 0, because we're always going to start drawing from y equals 0, right? Then frame width and frame height, they're never going to change. In fact, the only thing that changes is where in the x direction that you start the rectangle. So the first frame, frame 0, is going to be 0 times fw, which of course is 0, and then 0 again for the y. So it starts at 0, 0, which is the top left corner of the image, right? And then frame width and frame height. So 0, 0, frame width, frame height. Frame 1 is going to be 1 times frame width, which is just frame width, and then 0 frame width and frame height, etc., for every frame of animation, right? So all you got to do is somehow figure out which frame of the animation I should currently be drawing, specify the rectangle, tell the sprite to set that rectangle, and then whenever you draw the sprite, it'll be drawing the correct thing. So how are we going to implement that? Well, we're going to make an animation class. We make classes for everything, right? It's just easy to do. It's not the only way to do it. What we could do, if we wanted to adhere purely to pure data ECS, is write an animation system. Then that system would live in the gameplay class, or in the scene. And so the animation system would go through and manage all of that. But it turns out there's a lot of bookkeeping there, so I've made this sort of one exclusion where we're going to have an animation class that lives inside a component, but the animation class inside the component is going to have the logic that updates the frame for us, okay? Just because it would be like an order of magnitude more annoying if we didn't do it that way. So the animation class is going to store all the variables related to the animation that we just talked about with an update function that provides logic to progress the animation. And so we're going to call it the cAnimation component is going to store an instance of an animation object. And then it's a very slight departure from the pure data only in the component, but technically it's not the component that has the logic, it's the animation class, right? So the animation implementation, we are going to have some variables. One is called frame count. That is the number of frames in the animation. So for the Mega Man example we just gave, that would be 3. And game frame here means how many frames has this animation existed for in our game. So for example, if our game is running at 60 frames per second, and this animation has been around for 3 seconds, this variable will be at 60 times 3, 180. Okay, someone was awake, thank you. We're going to have a vec2 size, and this is going to be the size of the rectangle that we want to draw. And so this is just the whole width of the texture divided by the frame count, right? Because if there's 3, we want 1/3 of it, and then texture height. Then there's a variable called animation speed, and maybe this should be called animation duration. I keep forgetting to change it every year. But what it means is if animation speed is set to 10, what that means is every 10 frames, we're going to go to the next animation frame. So the word frame here is overloaded. I apologize. That's all you can do. But if animation speed is 10, it means that for game frames 0 through 9, it's drawing the first frame of Mega Man. Then 10 through 19, it's drawing the second frame of Mega Man, right? So if it's 60 frames per second and animation speed is 10, how often are we changing the animation frame every second? 6 times, right? So you can play with that variable, because if you're just changing the frame every frame, it'll just like, and you won't be able to see it. You've got to give the player enough time to actually register, oh, you know, you've got to play around with that variable. So each frame, what's going to happen? And I'm going to give you a skeleton animation class, and you're going to implement this function. But you're just going to implement it once, and then assignment 4, I'll give you a new one. So every update frame, I'm going to increment the number of frames that this has been alive. That's game frame plus plus. Then I'm going to calculate the frame of animation of Mega Man running, 0, 1, or 2, that I want to be drawing. And that is just the current amount of time I've been alive divided by that speed, mod the frame count. Why do I mod it? Because, you know, if I've been alive for several seconds, I might say frame 20. But frame 20 is actually 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Like, you have to mod it so that it goes, it's integer remainder division, right? So mod just makes it wrap around back to the beginning. Then I specify the rectangle, which is the formula that we just talked about. And then I just set the textured rect of the sprite to that rectangle. So that's how we do animations. The sprite doesn't change. The texture doesn't change. The only thing that changes is the subrectangle of that texture that we want to draw. Now, just realize that this is not the only way to do it. This is just a balance between a bunch of different things. The most important thing for me is that it's usable and it's relatively quick. There's not many ways that you can do this faster, right? And so we're going to make an animation class for that, and I've got a preview of that in a slide or two. No, I don't. So we'll just have I'll go over that when I introduce assignment 3. So the animation specification are going to be stored in an assets file. And an example, this is the actual full 4 frames of animation of Mega Man's texture, or Mega Man's running animation. So an animation then is going to require 2 separate things in our assets configuration file. One is the texture that the animation is going to be taken from. So I'm going to specify texture, tech run, and then the path to that. And so run 64 just means that it's 64 by 64 pixels. That's going to be the size of Mega Man. And then once I've loaded that texture, the animation is now going to specify which texture that it's taken from. So this animation is going to be called run. And the next thing is the name of the texture that I'm going to look up when I do that. The next integer is going to be the number of frames in that animation, which is 4, and then it's the speed of the animation, which means every 10th frame I'm going to go to the next, every 10th game frame I'm going to go to the next animation frame. So that's what we're going to have. We're going to have a bunch of these in our assignment. We've got a game engine already, right? I know it's a bit much, but you understand it all now, right? You could all program this. You're not going to be making all of that. Like, basically, what you are going to be doing for assignment 3, if memory, don't take my word for it right now. Take my word for it when I say it in the actual assignment lecture. But entity, done for you. Entity manager, done for you. You are going to be implementing the derived gameplay scene for this Mega Man type game, right? I'll show you just a quick preview of what you're going to be doing. And you are going to be implementing the animation class and the physics class. So the physics class is where you do the collisions that we talked about in the last lecture, which the video is now online. So physics, gameplay, and animation. That is basically all that you're going to be implementing for assignment 3. But I say all, it's still a decent chunk of coding, right? Games just require a bunch of coding. And I highly recommend going to check out these videos because one, it's called The Importance of Keyframes and Run Cycles. And what that is it talks about, like, for example here, Mega Man has 4 frames of animation. You might think that intuitively, if we have paid an artist enough money to draw 30 frames of animation so that it's super smooth running, right? And we have the processing power to do it, that 30 frames of animation would just be better than 4 frames of animation. This video talks about how that is not necessarily the case. And so I recommend watching that. And the second one, how old school graphics works, it talks about how sprite hardware used to work, how, you know, video memory used to work, etc. So I recommend watching them. They're not like absolutely required, but I think, you know, if you're interested in game programming in the modern era, knowing how it worked before is a very important tool to have. And really quickly, what I want to show you is the thing that we'll be implementing. I think I've already showed a demo of this, but here's the game. We've got a menu scene. In this menu scene, I can select between different levels, right? And I can hit a button to load it. Now I'm going to close the GUI for now, but what we've got is this crossover game where I have Mega Man running around inside a Mario level. So we're going to have these levels that you're going to, all of that level stuff, so like where all the tiles are, the different types of tiles, that level is specified as in there's a brick at this position. There's a pipe at this position. So the level file, you're going to implement the loading of that and then the drawing of it to the screen and all of the gameplay mechanics which involve running, collisions. So I can collide on top of this. I no longer fall down. If I hit a question mark, it becomes grayed out and a coin animation appears, right? If I hit a brick, it gets destroyed and a thing appears. I can shoot bullets. If it hits a pipe, nothing happens. If it hits a brick, I kill it, right? So we're going to be using all the things. And you can see, you know, this 4 frames of animation. When I jump, there's a different animation than when I'm standing. When I'm facing left versus facing right. Do I need 2 different textures for that? No, it turns out we can just flip textures in interesting ways. We're going to have like the end of levels and stuff like that. So, oh yeah, and if I hit these again, oh, I don't need to jump around. Nothing happens the second time that I hit them. How do I play that animation and then have it disappear? Oh, we can just attach a lifespan. Like interesting things like this, right? So this is the game that we're going to be making for assignment 3, and we've almost got all the tools for it. So I always look forward to seeing what people do for this one. It turns out that the hardest thing in this assignment is probably getting the physics exactly right and like not getting stuck on the wall when you jump up like this, right? So we've got this thing in the game where I can turn off the textures. That's a grid. There. So this is what the game sees, right? These are the entity outlines. These are the collision boxes for the entities. So this is all the game sees. Let me see if I can shoot, right? So we've got all these debug things. We've got a nice scene up here that allows me to see all the different assets that I've loaded, my entities, etc. So we're getting pretty close to a nice game engine. Like you can immediately take assignment 3 and just like start the project from assignment 3. Now I wouldn't recommend that because there's other things that we're adding in assignment 4. So I would wait for assignment 4. But you can see, like in only a few lectures of explaining this architecture, we've got something really kind of powerful and efficient and something that you can make any sort of 2D games in.